Hold your hand up in front of you and look at the space between your fingers. Your intuition tells you there's nothing there, just empty air. And if you removed all the air molecules and dust particles, nothing would remain, simply a void, an absence of stuff. Your intuition is wrong. That space between your fingers, even in the most perfect vacuum physicists can create, teems with activity, with fields fluctuating and energy bubbling up and subsiding, and forces exchanging in ways that have nothing to do with familiar atoms and molecules. At scales so small that even protons look like vast continents by comparison, physicists suspect that space itself might be churning and rippling in ways we're only beginning to understand. This is what modern physics tells us about empty space, and it stands as one of the strangest, most counterintuitive pictures to emerge from a century of quantum mechanics and quantum field theory. The idea that vacuum equals nothing, that emptiness is featureless, that space without matter serves as just an inert stage on which events play out, turns out to be incomplete at best and misleading at worst. That's what this video is about. We're going to explore what physicists actually mean when they talk about the quantum vacuum, why empty space is never really empty, what zero-point energy and vacuum fluctuations are and what they're not, and how a phenomenon called the Casimir Effect proves that these aren't just theoretical abstractions, but measurable realities with observable consequences. We'll push even further after that to a speculative idea called quantum foam, a picture of what spacetime itself might look like at the absolute smallest scales, where even the distinction between space and time becomes uncertain. By the end of this journey, you'll understand why physicists say that nothing is actually something, why a perfect vacuum can exert a force, and why the very concept of empty space might need to be retired from our vocabulary. If you enjoy this kind of deep exploration, if you appreciate taking the time to really sit with ideas that challenge how you understand reality, consider subscribing to the channel, since it helps these explorations reach more curious minds and tells me this is the kind of content you want to see more of. Now, let's begin. Let me start with something familiar and work our way toward the strange. When you pump the air out of a container, you create what we call a vacuum, a word coming from the Latin for empty. And in everyday terms, a vacuum is simply a region with very little matter in it. The vacuum of space, the vacuum in a light bulb, the vacuum inside a thermos, all represent regions where we've removed or excluded most of the particles that would otherwise occupy them. This is the classical concept of vacuum, the one that makes intuitive sense, where empty means nothing there and vacuum means absence of stuff. For most of human history, this served as the only concept of vacuum anyone needed. Even in physics, for centuries, the vacuum was treated as simply the stage on which physical events occurred, with matter moving through empty space and forces acting across empty space, while the space itself remained featureless, inert, a background that didn't participate in the physics. That began to change in the 20th century with the development of quantum mechanics and then quantum field theory. Let me explain what quantum field theory is, because understanding why empty space isn't empty requires it. Our everyday experience suggests the world consists of particles, discrete little objects that have locations and properties. with electrons orbiting nuclei, protons and neutrons clustering in atomic cores, and photons carrying light from place to place. This particle picture is useful and intuitive. Quantum field theory offers a different and deeper picture, though. The fundamental entities in quantum field theory aren't particles, but fields. Fields that permeate all of space, everywhere, at all times. Think about what a field means. A magnetic field isn't located at a single point, but exists throughout a region of space with a value at every location. And an electric field works the same way. Quantum field theory proposes a field for every type of particle: an electron field, a photon field, a quark field. And all of these fields fill all of space. What we call particles are excitations of these fields. A photon isn't a little ball of light traveling through space, but rather a vibration, an excitation, a ripple in the electromagnetic field. An electron isn't a tiny charged marble, but an excitation of the electron field. This might sound like a semantic distinction, but it's not, since the field picture has consequences that the particle picture lacks. And one of those consequences is that empty space becomes impossible in a very precise sense. Here's why. Quantum mechanics includes a principle called the Heisenberg Uncertainty Principle, formulated by Werner Heisenberg in 1927, which states that certain pairs of properties, called conjugate variables, cannot both be precisely known at the same time. The most famous version involves position and momentum. The more precisely you know where a particle is, the less precisely you can know how fast it's moving, and vice versa. The mathematical statement holds that the product of the uncertainties in position and momentum must be at least half of Planck's reduced constant. Delta x times delta p is greater than or equal to limitus over 2. This isn't a limitation of our measuring instruments, but a fundamental feature of quantum systems, with the uncertainty built into the fabric of reality itself. Now, apply this to fields. A quantum field has values at every point in space, and those field values are quantum mechanical variables subject to the uncertainty principle. For the field to be completely empty would mean the field value is exactly zero everywhere, with no fluctuation and no variation. But that would also require the field to have exactly zero momentum in a certain technical sense. The uncertainty principle forbids this. You cannot have a quantum field that is both exactly zero and exactly still, meaning there must be some residual fluctuation, some irreducible jiggling, even in the lowest possible energy state. This lowest possible energy state is called the vacuum state, and the fluctuations that remain even in this ground state are called vacuum fluctuations or zero-point fluctuations. Let me give you an analogy that might help. Think about a simple pendulum, like a swing on a playground. Classical physics says the lowest energy state of the pendulum occurs when it's hanging straight down, perfectly still, with zero motion and zero energy of motion. Quantum mechanics makes this impossible, though. A quantum pendulum cannot be both perfectly positioned and perfectly still. And even in its ground state, the lowest energy state, some residual motion remains. The pendulum jiggles a tiny bit, possessing what physicists call zero-point energy, the energy of these irreducible ground state fluctuations. The mathematical expression for this is simple and elegant. For a quantum harmonic oscillator, the ground state energy equals 1/2 times egrana times omega, where omega represents the oscillation frequency, and this 1/2 egrana omega is the zero-point energy, the energy that remains even when the system is as quiet as quantum mechanics allows. Now extend this to fields. A quantum field can be thought of as an infinite collection of harmonic oscillators, one for each possible vibration mode. And each of these oscillators has its own zero-point energy. The vacuum state of the field occurs when all these oscillators occupy their ground states, but each one still has that irreducible 1/2 egrana omega of energy. This is what physicists mean when they say the vacuum has energy. The quantum vacuum isn't nothing, but the lowest energy state of quantum fields. And that state still has structure, still has fluctuations, still has energy. I remember the first time I truly understood this, and I had to put down the book and just sit with it for a while. The idea that emptiness has a structure, that nothing is actually something, that the vacuum is a defined quantum state rather than the absence of a state, is one of those concepts that takes time to absorb. Let me be careful about something though, because this is a topic where it's easy to slip into misleading language. You've probably heard phrases like virtual particles popping in and out of existence to describe vacuum fluctuations. This visualization connects to how physicists actually calculate things using Feynman diagrams, where virtual particles appear as internal lines representing quantum processes. Virtual particles are not the same as real particles, though. They're not directly observable in the way that a photon hitting your eye or an electron registering in a detector is observable. And the language of particles popping in and out of existence serves as a vivid metaphor, a calculational shorthand, but can create a misleading picture of literal particles appearing from nothing and then disappearing. What's actually happening is more subtle. The quantum fields are fluctuating. The field values are not exactly zero even in the vacuum state, and these fluctuations are described mathematically by the Uncertainty Principle and the properties of quantum field theory. Whether you call them virtual particles or vacuum fluctuations or zero-point activity, the underlying physics remains the same. What matters is that these fluctuations are not just theoretical abstractions, since they have measurable consequences. And the most famous of those consequences is the Casimir Effect. Now let me tell you about the Casimir Effect, because this is where abstract quantum field theory meets concrete laboratory reality. 1948 brought a Dutch physicist named Hendrik Casimir making a prediction that seemed almost impossible. He calculated that two perfectly conducting metal plates, placed parallel to each other in a vacuum with nothing between them, no charge, no magnetic fields, no particles of any kind, would nonetheless experience a force pulling them together. Think about how strange that is. Two neutral pieces of metal in a perfect vacuum with nothing connecting them, and yet they attract each other. Not because of gravity, which would be far too weak to measure at laboratory scales. Not because of electric charge, because the plates are neutral. Not because of any ordinary force that classical physics would predict. Casimir showed that the force arises from the quantum vacuum itself. Here's the physical picture. The electromagnetic field, like all quantum fields, has vacuum fluctuations that can be thought of as all possible vibration modes of the field, each with its zero-point energy. In empty space, far from any boundaries, all wavelengths of fluctuation are equally allowed. Now put in the two metal plates. Those plates act as boundaries for the electromagnetic field, constraining which fluctuation modes can exist between them, so that only wavelengths that fit between the plates, that satisfy certain boundary conditions, are allowed in that region. Outside the plates, all wavelengths remain allowed, while inside only some are. This creates an asymmetry. The vacuum fluctuation modes outside the plates differ from those inside. This difference in the modes creates a difference in energy density, and that difference in energy manifests as a force pushing the plates together. Let me give you an analogy. Think about a guitar string. When you pluck an open string, it can vibrate at many frequencies, its fundamental frequency and all the harmonics. Touch the string lightly at a node point, though, and you've changed the boundary conditions so that only certain vibration modes are now allowed, with the spectrum of possible vibrations having changed. The Casimir effect works the same way. The conducting plates change the boundary conditions for the electromagnetic field. The spectrum of allowed vacuum fluctuations differs between the plates than outside them, and that difference produces a measurable force. The mathematical formula for the Casimir force between two ideal parallel conducting plates is precise. The force per unit area equals pi squared times chi times c divided by 240 times the separation distance to the fourth power. That fourth power dependence on distance matters, because it means the force is extremely weak at large separations, but grows very rapidly as the plates get closer together. Let me put some numbers on this. At a separation of 1 micrometer, 1/1,000,000th of a meter, the Casimir pressure measures about 1.3 times 10 to the negative third pascals, or about 1.89 times 10 to the negative 7th pounds per square inch, which is tiny, barely detectable. 10 times closer, at a separation of 100 nanometers, the pressure jumps to about 13 pascals, roughly 0.00189 pounds per square inch, which remains small but becomes measurable with sensitive instruments. Another factor of 10 closer, at a separation of 10 nanometers, the pressure reaches about 130,000 pascals, roughly 19 pounds per square inch, which is comparable to the pressure of a finger pressing on a surface. This explains why the Casimir effect proved so hard to measure for so long. At everyday distances, the force is negligible, and you need to get plates extremely close together into the nanometer regime before the effect becomes experimentally accessible. For nearly 50 years after Casimir's prediction, experimental verification remained elusive. Early attempts, notably by Marcus Sparnay in 1958, reported results consistent with Casimir's prediction. But the precision era really began much later. 1997 brought Steve Lamoureux at the University of Washington performing a landmark experiment. Using a sphere and a plate rather than two parallel plates, Lamoureux measured the Casimir force at separations ranging from about 0.6 to 6 micrometers with unprecedented precision, and the results matched Casimir's prediction. 1998 brought Umar Mohideen and Anushree Roy pushing even further, using an atomic force microscope to measure the Casimir force at separations down to 100 nanometers. And again, the results confirmed the theory. Since then, Casimir physics has become a precision science. A 2009 review in Reviews of Modern Physics by Kimchitskaya, Mohideen and Mostepanenko summarized decades of experiments, accounting for complications like finite conductivity, temperature effects, surface roughness, and electrostatic patch potentials. The Casimir effect is real, measured, and not controversial. Think about what this means. You have two pieces of metal in a vacuum with nothing between them in the classical sense, no particles, no radiation, no forces we would have recognized before quantum mechanics, and yet they push toward each other. The force comes from the quantum vacuum itself, from the difference in vacuum fluctuation modes created by the presence of the boundaries. This is the part that still amazes me, even after years of studying this topic. The vacuum isn't nothing, but something, a quantum state with properties that can be modified by boundaries and materials. And those modifications have measurable physical consequences. I need to be careful about interpretation here, though, because the Casimir effect is sometimes presented in misleading ways. You may have heard the Casimir effect described as energy from nothing, or proof that the vacuum contains infinite energy, or similar dramatic claims. These interpretations go beyond what the physics actually supports. 2005 brought physicist Robert Jaffe at MIT publishing an influential analysis clarifying what the Casimir effect does and does not prove about vacuum energy. What we measure is a force, which corresponds to a difference in energy between different configurations, and the absolute value of the vacuum energy is not directly observable, since it can be shifted by a mathematical procedure called renormalization without changing any physical predictions. This is a subtle but important point. The Casimir effect demonstrates that vacuum fluctuations have physical consequences, that boundary conditions matter, that the quantum vacuum responds to the presence of materials in measurable ways. What it doesn't do is tell us the absolute energy content of the vacuum, which remains one of the deep, unsolved problems at the intersection of quantum field theory and gravity. When you hear claims about the vacuum containing enormous energy that could somehow be tapped for unlimited power, be skeptical, since the physics is more subtle than those claims suggest. What we can say with confidence is this: the quantum vacuum is not nothing. It has structure, it responds to boundaries, and its properties can be measured. The Casimir effect proves that the old picture of empty space as featureless void is inadequate. Let me take you even further now, beyond the static Casimir effect, to something even more dramatic. Shaking the boundaries produces different effects than keeping them stationary. In the standard Casimir effect, the plates are stationary, modifying the vacuum fluctuation modes in a static way, and the result is a static force. Move the boundaries fast enough to disturb the vacuum fluctuations dynamically, though, and something else happens. This is the Dynamical Casimir Effect, and for a long time it remained purely theoretical. The idea holds that if you oscillate a boundary fast enough, faster than the vacuum fluctuations can adiabatically adjust, you can convert vacuum fluctuations into real photons. The boundary essentially shakes loose radiation from the vacuum itself. The challenge is that fast enough means speeds approaching the speed of light, and you cannot physically move a mirror at such speeds, which meant the Dynamical Casimir effect remained a theoretical curiosity for decades. 2011 brought a team led by Christopher Wilson achieving something remarkable. They didn't move a physical mirror, but instead used a superconducting circuit, a device called a squid, to create an effective boundary whose position could be changed at a significant fraction of the speed of light by modulating electrical properties rather than physically moving material. When they ran the experiment, they detected real photons, radiation that came from nowhere except the vacuum fluctuations being disturbed by the rapidly modulating boundary. The Dynamical Casimir effect had moved from theory to experimental reality. This is profound. The vacuum fluctuations, which might otherwise seem like mathematical abstractions, can be converted into real, detectable radiation, with the boundary shaking the vacuum and light coming out. Let me invite you to really sit with this for a moment. The space around you, right now, is not empty. Quantum fields permeate everything, and those fields have fluctuations even in their lowest energy state. Under ordinary circumstances, you don't notice these fluctuations because they don't interact with ordinary matter in obvious ways. Put in the right boundaries, though, metal plates at nanometer separations, and the fluctuations manifest as a measurable force. Shake those boundaries fast enough, and the fluctuations become real radiation. The vacuum is active. The vacuum responds, and the vacuum has properties. This is what modern physics tells us about empty space, one of the most surprising revisions in our understanding of reality, emerging from the mathematics of quantum field theory and confirmed by careful laboratory experiments over decades. Now let me give you a sense of scale, because the numbers involved in this physics are so extreme that they're hard to grasp without perspective. The Casimir effect operates at what we might call the nano world. A typical Casimir experiment involves separations of 10 nanometers to 1 micrometer. And to put that in perspective, a human hair is about 50 to 100 micrometers thick. A 100 nanometer gap, where the Casimir effect becomes readily measurable, is about 1,000 times thinner than a human hair. This is small by human standards, but it's enormous by the standards of fundamental physics. The Planck length, one of the fundamental constants of physics, measures 1.616255 times 10 to the negative 35 meters, or about 6.36 times 10 to the negative 34 inches. This number comes from combining the fundamental constants of quantum mechanics, gravity, and special relativity, and it represents the scale where quantum effects on space-time itself might become important. Before I tell you the next number, take a guess at how many Planck lengths fit in the radius of a single proton. The proton, the tiny particle at the heart of every hydrogen atom, has a radius of about 8.414 times 10 to the negative 16 meters. That sounds small, and it is small, since you'd need about 1 trillion protons lined up to span a millimeter. Now compare that to the Planck length. The ratio comes out to about 5.21 times 10 to the 19th power, about 50 quintillion, 50 billion billion, meaning the proton is 50 quintillion times larger than the Planck length. Let me put that in perspective. If you scaled the Planck length up to 1 millimeter, which you could see with your naked eye, then at the same scale, the proton would measure about 5.2 times 10 to the 13th meters across, 52 trillion meters, about 347 astronomical units, far beyond the orbit of Pluto, out into the frozen reaches of the outer solar system. From a millimeter to beyond Pluto, that's the ratio between the Planck length and a proton. The Bohr radius, the characteristic size of a hydrogen atom, is even larger. At 5.29 times 10 to the negative 11 meters, it measures about 3.27 times 10 to the 24th power times the Planck length. More than 3 septillion. These numbers are staggering. They tell us that the realm of Planck-scale physics, where quantum gravity effects might dominate, is so far removed from even the smallest structures we can probe experimentally that we might as well be trying to see atoms from the moon. This matters because there's a speculative idea in physics called quantum foam, or spacetime foam, and it operates at the Planck scale. Let me tell you about quantum foam. Everything we've discussed so far, vacuum fluctuations, zero-point energy, the Casimir effect, takes place within a framework where space-time itself is classical. The fields fluctuate, but they fluctuate on a fixed space-time background, with space and time remaining smooth, continuous, and well-behaved. The quantum weirdness lives in the fields, not in the stage they occupy. Quantum foam represents a different idea, the speculation that space-time itself might have quantum fluctuations at the Planck scale, that the smooth fabric of space and time might break down into something frothy, foamy, chaotic at the smallest possible scales. The idea traces back to John Wheeler, one of the great physicists of the 20th century. 1955 brought Wheeler publishing a paper on geons, hypothetical gravitational objects, and he later developed broader ideas about what he called geometrodynamics, the dynamics of geometry itself. Wheeler proposed that at the Planck scale, space-time might not be smooth at all, but constantly fluctuating, with the geometry itself uncertain, bubbling, forming tiny wormholes and handles and other topological features that appear and disappear on timescales of about 10 to the negative 44 seconds, the Planck time. Wheeler called this picture space-time foam. Think about the surface of a calm lake. From a distance, from an airplane looking down, the surface looks perfectly smooth, flat, featureless. Getting closer, you start to see ripples, waves, texture. Get close enough, and you can see individual water molecules jiggling around. The surface no longer smooth at all, but chaotic at the molecular scale. Space-time foam applies a similar idea to space and time themselves. From our everyday perspective, and even at the scale of atoms and subatomic particles, space-time looks smooth and continuous. Zoom in far enough, though, down to the Planck scale, and space-time itself might become rough, uncertain, foamy. I want to be very clear about something here. Quantum foam is speculative and not experimentally confirmed. Unlike the Casimir effect, which is measured and verified, quantum foam remains a theoretical idea about what might happen at scales we cannot currently probe. The reason it stays speculative is that we don't have a complete theory of quantum gravity. We have quantum field theory, which describes the quantum behavior of fields on a classical space-time background. We have general relativity, which describes the classical behavior of space-time in response to matter and energy. What we lack is a fully consistent theory that combines both. A theory that would tell us definitively what space-time looks like at the Planck scale. Various approaches to quantum gravity exist, including string theory, loop quantum gravity, causal set theory, and others. And they make different predictions about Planck scale physics. Some support something like Wheeler's foam picture, while others suggest space-time might remain smooth or have different properties at small scales. The physics community is actively working on this, but the answer isn't in yet. What we can do is test certain predictions that some quantum foam models make, and this is where some recent work comes in. 2015 brought a team led by Vlasios Vassileou using data from the Fermi Large Area Telescope to constrain what's called Planck-scale space-time fuzziness. The idea holds that if space-time has quantum fluctuations at the Planck scale, those fluctuations might affect the propagation of light over cosmological distances. Think about a gamma-ray burst, one of the most energetic events anywhere, occurring billions of light-years away. Photons from that burst travel across vast stretches of space to reach our detectors. And if space-time is fuzzy at the Planck scale, different photons might experience slightly different path lengths or travel times depending on their energy. Higher energy photons might interact more strongly with the space-time fluctuations, arriving at slightly different times than lower energy photons. By analyzing the arrival times of photons from gamma-ray bursts across a range of energies, Vassileou and colleagues placed limits on certain models of space-time fuzziness. They found that some models, the ones predicting the strongest effects, were ruled out, and space-time appears to be smooth down to scales very close to the Planck length, at least in the ways those particular models predicted. This doesn't prove that quantum foam doesn't exist, but constrains certain versions of the idea, while other models remain compatible with the observations. What it shows is that we're not entirely in the dark, and can use astrophysical observations to test at least some aspects of Planck-scale physics, even though we can't build accelerators that reach those energies or microscopes that resolve those distances. A 2023 review by physicist Steve Carlip summarized the current status of space-time foam ideas in the context of quantum gravity. The picture remains unresolved, with quantum foam standing as a fascinating possibility, but not a confirmed feature of reality. This is the frontier, where our understanding becomes uncertain. We know that the quantum vacuum of fields is not nothing, that vacuum fluctuations are real and have measurable consequences. What we don't know is whether space-time itself, the stage on which fields live, also has quantum properties at the smallest scales. The distinction matters. Vacuum fluctuations of quantum fields on a classical space-time background represent established physics confirmed by the Casimir Effect and the Dynamical Casimir Effect. Quantum fluctuations of space-time itself, the foam picture, remain speculative, constrained by observation but not confirmed. When you read about quantum foam or space-time foam, keep this distinction in mind. It's an idea worth exploring, a possibility worth considering, but it's not the same as the solid experimental ground of vacuum fluctuations and the Casimir effect. Let me walk you through the historical timeline of how these ideas developed, because seeing how understanding builds over time helps clarify the physics. The story begins in 1927, when Werner Heisenberg published his paper on the Uncertainty Principle. This was a foundational moment for quantum mechanics, establishing that certain pairs of physical quantities cannot both be precisely known simultaneously, including position and momentum, energy and time. The uncertainty is not a failure of measurement, but a fundamental feature of quantum systems. At first, the uncertainty principle applied to particles. You can't know both where the electron is and how fast it's moving. Not exactly. As quantum field theory developed through the 1930s and 1940s, though, physicists realized that fields are also quantum mechanical objects, subject to the same principles, which meant the vacuum state of those fields couldn't be perfectly empty in the classical sense. 1948 brought Casimir's prediction. Working at the Philips Research Laboratories in the Netherlands, Hendrik Casimir calculated that two perfectly conducting parallel plates in a vacuum would experience an attractive force due to the modification of electromagnetic field modes between them. This was a purely theoretical result at the time, based on quantum electrodynamics, the quantum field theory of electromagnetic interactions. For decades, Casimir's prediction remained mostly theoretical. Early experimental attempts, like Sparnay's work in 1958, provided results consistent with the prediction, but lacked the precision to be definitive. 1955 brought Wheeler developing his ideas about geometrodynamics and proposing the space-time foam picture. Speculative physics thinking about what quantum gravity might look like decades before any experimental constraints existed. Wheeler was imagining what happens when you push quantum mechanics to its logical extreme, applying it not just to fields on space-time, but to space-time itself. The precision era for Casimir physics began in the late 1990s. Lamoureux's 1997 experiment was a watershed moment, demonstrating the Casimir force with enough precision to distinguish it from other effects and confirm Casimir's 50-year-old prediction. Mohideen and Roy's 1998 atomic force microscope measurements pushed to even smaller separations, further confirming the theory. The 2000s and 2010s saw Casimir physics mature into a precision science. The 2009 Review of Modern Physics article, Klimchitskaya, Mohideen, and Mostepanenko, synthesized decades of work accounting for all the complications that arise with real materials: finite conductivity, temperature effects, surface roughness, geometry, and more. The Casimir effect was no longer a curiosity, but a well-characterized phenomenon with practical implications for nanotechnology and micro-electromechanical systems. 2005 brought Jaffe's clarification about what the Casimir effect does and does not prove regarding vacuum energy, distinguishing between what can be measured and what remains subject to interpretation. 2011 marked another landmark year, with Wilson and colleagues observing the Dynamical Casimir effect in a superconducting circuit. This was the first laboratory demonstration that vacuum fluctuations could be converted into real photons by rapidly changing boundaries, and the theoretical prediction, which had seemed almost impossibly demanding experimentally, was achieved through clever engineering using superconducting technology. On the quantum gravity front, 2015 brought the Fermi-Lat constraints on space-time fuzziness by Vasileu and colleagues. This was a beautiful example of how astrophysical observations can test physics at scales far beyond what any laboratory could probe, with gamma-ray bursts becoming a tool for investigating Planck-scale physics. Here we are now in the 2020s, with ongoing work on both fronts. Casimir physics continues to advance, with applications in nanotechnology and fundamental tests of quantum electrodynamics. Quantum gravity remains an open problem, with space-time foam, one of many ideas, being explored and constrained. This timeline reveals something about how physics works. Ideas emerge from theory sometimes decades before they can be tested, and experiments gradually catch up, confirming some predictions and ruling out others. The frontier keeps moving. Now, let me address some common misconceptions, because this is a topic where popular accounts often go astray. First, about virtual particles. You've probably seen animations or descriptions showing pairs of particles spontaneously appearing from the vacuum and then annihilating. This visualization serves certain purposes, but it can mislead if taken too literally. In quantum field theory calculations, virtual particles appear as internal lines in Feynman diagrams, representing contributions to a calculation, not particles that could be detected or counted. A real particle is something that can be measured, that carries energy and momentum to a detector. A virtual particle is a mathematical device for organizing a quantum calculation. The vacuum fluctuations are real in the sense that they have physical consequences, like the Casimir force. The picture of little particle-antiparticle pairs popping in and out of existence like bubbles in a fizzy drink is more metaphor than physics, though, capturing something about the calculations but not the underlying ontology. Second, about zero-point energy and free energy claims. You may have encountered claims that the vacuum contains vast amounts of energy that could be tapped for unlimited power. These claims dramatically overstate what the physics supports. Yes, quantum field theory assigns a zero-point energy to the vacuum modes. But the absolute value of this energy is not directly observable, since what matters physically are energy differences. When you try to extract energy from the vacuum, the constraints of thermodynamics and quantum mechanics apply. The Casimir effect doesn't provide free energy because the force does work as the plates move together, but you'd have to do work to separate them again. There's no perpetual motion machine hiding in the quantum vacuum. Third, about quantum foam and space-time breaking down. Some popular accounts suggest that quantum foam means space-time becomes meaningless at small scales, that physics itself dissolves into chaos at the Planck length. This goes beyond what the speculative models actually claim. Even in Wheeler's foam picture, space-time has structure. It's just that the structure fluctuates. Different proposed quantum gravity theories suggest different pictures of Planck scale physics, some involving foam-like fluctuations, others involving discrete space-time structures, others maintaining approximate smoothness with quantum corrections. What space-time really looks like at the Planck scale remains open. When you hear dramatic claims about the quantum vacuum or space-time foam, it's worth asking whether this is based on established physics, like the Casimir effect, or on speculative extrapolation into regimes we can't yet test. Let me spend time now thinking about what all this means, what the implications are for our understanding of reality. The classical picture of empty space as a featureless void is comfortable and intuitive. Space is where things happen, serving as the stage rather than an actor. Remove all the matter and radiation and forces, and what's left is nothing, empty, blank. Quantum field theory tells us this picture is incomplete. Space is permeated by fields. Those fields have a quantum nature, and even in their lowest energy state, they fluctuate. These fluctuations can be modified by boundaries and materials, and those modifications have measurable consequences. This doesn't mean space is full of stuff in the everyday sense. It's not like the vacuum is crowded with particles the way a room is crowded with air molecules. The vacuum is the ground state, the quiet state, the state from which you can't extract any more energy by ordinary means. It's a quantum mechanical state, with properties though, not an absence of properties. In classical physics, nothing was easy to define. No matter, no energy, no fields, no forces, just empty space. In quantum field theory, you can define a lowest energy state, but that state is not featureless. It has structure, responds to boundaries, and can be probed and measured. Is that nothing? In some sense, yes, it's as close to nothing as physics allows. In another sense, no, because there's still something there, still properties, still physics. This might seem like philosophical hair-splitting, but it has practical consequences. The Casimir effect is real, and nanoscale devices have to account for it. The dynamical Casimir effect has been observed. These are engineering realities, not just abstract puzzles. If quantum foam turns out to be correct, if space-time itself fluctuates at the Planck scale, then nothing becomes even more problematic. You can't have empty space if space itself is uncertain, can't have a featureless void if the geometry is fluctuating. We may need to retire the concept of nothing from physics altogether, or at least radically revise what we mean by it. Let me take you deeper into some of the physics now, because understanding the details helps you appreciate how remarkable these phenomena are. The Casimir force formula is worth examining closely. For two ideal parallel conducting plates, the force per unit area equals pi squared times EML times c, all divided by 240 times the separation distance to the fourth power. Let me unpack that. The factor of pi squared over 240 is a pure number coming out of the mathematics of summing over field modes. It has no deep physical meaning, but is simply what the calculation gives. The EML is Planck's reduced constant, the fundamental quantum of action, and its presence tells you this is a quantum effect. In classical physics, EML doesn't appear, and there's no Casimir force for classical fields. The c is the speed of light, appearing because we're dealing with the electromagnetic field, which propagates at c. The distance to the fourth power in the denominator represents the crucial dependence, with the Casimir pressure scaling as 1 over a to the fourth. Double the distance, and the pressure drops by a factor of 16. Halve the distance, and the pressure increases by a factor of 16. This fourth power scaling explains why the Casimir effect is irrelevant at everyday scales, but dominant at nanometer scales. At a separation of 1 meter, the pressure is utterly negligible. At 1 micrometer, it's measurable. At 10 nanometers, it's substantial. In the nano world, the quantum vacuum becomes a significant player. The actual experiments are more complicated than the idealized theory, and that's where much of the interesting physics lives. Real materials are not perfect conductors, having finite conductivity, which means the electromagnetic field can penetrate a small distance into the material, rather than being perfectly reflected at the surface. This modifies the Casimir force, and the modification depends on the specific properties of the material. Real experiments also have to deal with geometry. The original Casimir calculation was for infinite parallel flat plates, which is mathematically convenient but experimentally challenging. It's hard to keep large flat surfaces perfectly parallel at nanometer separations. So experimenters often use other geometries. A sphere near a flat plate, for instance, which is what Lamoureux used. The force depends on geometry, and correcting for geometrical factors is part of the experimental analysis. Temperature matters too. The original Casimir calculation was for 0 temperature, but real experiments happen at room temperature or close to it. Thermal fluctuations add to the quantum fluctuations, and at high enough temperatures, thermal effects can dominate over quantum effects. Surface roughness is another complication. Real surfaces are not perfectly smooth, having bumps and pits and variations at the nanometer scale that affect the local separation and thus the force. Careful experiments have to characterize and correct for surface roughness. There are also electrostatic effects. Even neutral conductors can have patch potentials, small voltage differences across the surface due to variations in work function or contamination. These create electrostatic forces that can be confused with the Casimir force if not carefully controlled. The fact that modern experiments can measure the Casimir effect at percent-level precision, accounting for all these complications, stands as an achievement of experimental physicists and shows the robustness of the underlying theory. Let me talk about the dynamical Casimir effect in more detail, because it's such a striking demonstration of vacuum physics. The static Casimir effect is about modified boundary conditions creating a force. The dynamical Casimir effect is about changing boundary conditions creating particles. The physics holds. But vacuum fluctuations are constantly present, with virtual photons of all wavelengths. These fluctuations normally don't produce real particles, because energy conservation would be violated. A virtual photon that becomes real would come from nowhere. Move a boundary fast enough, though, and you're effectively doing work on the field, pumping energy into the vacuum fluctuations. If the motion is fast enough, that energy can convert virtual photons into real ones. Fast enough means a significant fraction of the speed of light. For a physical mirror, this is essentially impossible, since you can't accelerate a piece of metal to near light speed in an oscillating motion. The breakthrough by Wilson and colleagues was realizing that you don't need to move a physical object. You can create an effective moving boundary by changing the electrical properties of a material. In a superconducting circuit, you can use a SQUID, a superconducting quantum interference device, to modulate the effective position of a boundary at very high frequencies. The field sees the boundary moving, even though the atoms stay put. When they ran this experiment in 2011, they observed real microwave photons coming out of the circuit. Photons that weren't there before, that weren't injected from outside, that came from the vacuum fluctuations being shaken loose by the moving boundary. The properties of the emitted radiation matched the predictions of Dynamical Casimir theory. The photons came in correlated pairs. Their frequencies were related to the oscillation frequency of the boundary, and the statistics were non-classical, consistent with squeezed vacuum states. This was not ambient thermal radiation, and not leakage from some external source. It was radiation produced by disturbing the quantum vacuum. When I first learned about this result, I had to put down the paper and just think about it for a while. A machine that converts nothing into something. Not nothing in the classical sense, but the quantum vacuum, the lowest energy state. Shake it hard enough and photons come out. The dynamic or Casimir effect reinforces the message of the static Casimir effect. The vacuum is not empty, has structure, and responds when you change the boundaries. Let me now address the connection between vacuum energy and cosmology, because this is one of the great unsolved puzzles in physics. In cosmology, there's a quantity called the cosmological constant, a term in Einstein's equations of general relativity that describes an energy density associated with empty space. Observations of the accelerating expansion of the universe suggest that this cosmological constant is non-zero but very small. You might think that vacuum energy from quantum field theory could explain the cosmological constant. After all, we've been discussing how the vacuum has energy, has fluctuations, has structure. Shouldn't that show up gravitationally? The problem is that when you try to calculate the vacuum energy from quantum field theory, you get numbers that are wildly, catastrophically, absurdly larger than the observed cosmological constant. The discrepancy measures about 10 to the 120th power, one of the largest disagreements between theory and observation in all of physics. This is called the cosmological constant problem, and it remains unsolved. Various proposed explanations exist. Perhaps different contributions to the vacuum energy cancel each other almost perfectly. Perhaps the vacuum energy doesn't gravitate in the way naive calculations suggest. Perhaps there's some selection effect related to the anthropic principle. No solution is generally accepted, though. The cosmological constant problem reminds us that while we understand a lot about vacuum physics, deep mysteries remain. The Casimir Effect tells us that vacuum fluctuations are real and have consequences. But exactly how vacuum energy couples to gravity and why the observed cosmological constant is so much smaller than quantum field theory calculations naively suggest remains a frontier question. This brings us back to the speculative terrain of quantum foam and quantum gravity. One reason physicists care about quantum gravity is the hope that it might shed light on puzzles like the cosmological constant problem. If space-time itself has quantum properties, if the geometry fluctuates at the Planck scale, then our current calculations of vacuum energy might be missing something important. We don't have a complete theory of quantum gravity, though, so we don't know what that something might be. String theory, one approach to quantum gravity, suggests that the fundamental entities are not point particles, but tiny vibrating strings. In string theory, the vacuum has a rich structure with many possible configurations, and some string theorists have proposed that the cosmological constant problem might be addressed through a landscape of possible vacua, with our universe occupying one particular vacuum state. Loop quantum gravity, another approach, suggests that space-time is discrete at the Planck scale, made up of tiny loops or networks. In this picture, the notion of a smooth vacuum might need to be replaced with something more granular. Causal set theory proposes that space-time is fundamentally a discrete set of points with causal relations between them, rather than a continuous manifold. These are all active research programs with different predictions about Planck scale physics. None has been experimentally confirmed, and the quantum nature of space-time remains an open question. What we can say is that the success of vacuum physics at accessible scales, the confirmation of the Casimir Effect, the observation of the Dynamical Casimir Effect, gives us confidence that quantum field theory works in regimes we can test. Extrapolating to the Planck scale is speculative, but it's speculation grounded in a successful framework. Let me talk about some of the practical implications of Casimir physics, because this isn't just abstract theorizing, but has real engineering consequences. In the world of micro and nano electromechanical systems, often abbreviated as MEMS and NEMS, the Casimir force is a significant design consideration. When you're building devices at the scale of micrometers and nanometers, with moving parts that come very close together, the quantum vacuum exerts forces that can't be ignored. Consider a tiny switch or actuator that has two surfaces approaching each other. At nanometer separations, the Casimir force can be strong enough to pull the surfaces together and stick them. This phenomenon, sometimes called stiction for static friction, is a real problem in nanotechnology. The quantum vacuum can gum up your tiny machines. Understanding the Casimir force opens possibilities, though. If you can control it, you might be able to use it. And there have been proposals for Casimir Effect actuators, switches, and sensors that exploit rather than fight the vacuum force. The key is understanding. Once you know the force exists and can calculate it accurately, you can design around it or with it. The precision measurements of the Casimir force over the past few decades have provided exactly this understanding. There's also ongoing research into modifying the Casimir effect using different materials and geometries. The force between two conductors is attractive, pulling them together, but theory predicts that with the right combination of materials, you might be able to create repulsive Casimir forces, pushing surfaces apart. Such repulsive Casimir effects have been observed in certain configurations involving liquids and specific material combinations. This is an active area of research, with potential applications in reducing friction and stiction in nanoscale devices. Beyond practical applications, there's fundamental interest in using Casimir measurements to test quantum electrodynamics at high precision. Any discrepancy between the measured force and the theoretical prediction could signal new physics, deviations from the standard model, or effects we haven't accounted for. No significant discrepancies have been found yet, with the theory working. The search continues, though, because precision tests are one of the ways we discover new physics. Let me now invite you to consider what all this means for how we think about the physical world. Before quantum mechanics, physics was fundamentally about objects, particles with definite positions and velocities, fields with definite values at each point. The world consisted of stuff, and the stuff had properties that could, in principle, be precisely known. Quantum mechanics introduced uncertainty, not as a limitation on our knowledge, but as a feature of reality itself. Particles don't have definite positions and momenta simultaneously. Fields don't have definite values and rates of change simultaneously. And the world is, at its foundation, fuzzy. The quantum vacuum is the ultimate expression of this fuzziness. Even when there's nothing there in the classical sense, when you've removed all the particles and cooled everything to zero temperature, there's still irreducible quantum activity. The fields fluctuate, the vacuum has energy, and the ground state is not featureless. This represents a shift in how we think about nothingness and emptiness. In quantum physics, there is no true emptiness, only the vacuum state, which is something rather than nothing. Think about the implications for questions like, why is there something rather than nothing? This is often framed as a deep philosophical puzzle. If physics tells us that nothing as classical emptiness is impossible, though, that the quantum vacuum is always there with its fluctuations and energies, then the puzzle looks different. I'm not saying physics answers the philosophical question, but it changes what we mean by the terms. The nothing of quantum field theory is richer than the nothing of classical intuition. Let me also address something about the limits of our knowledge. We've discussed vacuum fluctuations as if we understand them completely, and in a certain sense we do. Quantum field theory is a mature, well-tested framework. The Casimir effect can be calculated to high precision and matches experiment, and we have a mathematical structure that works. There's a deeper question we can't yet answer, though. What is the vacuum really? Is it made of anything? And what's actually happening when we say the fields are fluctuating? These are interpretational questions, somewhat analogous to the interpretational questions about quantum mechanics more broadly. The mathematics tells us what to predict, but it doesn't always tell us what story to tell about underlying reality. Some physicists are content with the mathematics, accepting that the predictions work and that's what matters. Others seek a deeper understanding, a picture of what's really going on beneath the equations. For the quantum vacuum, we don't have a universally agreed picture. The virtual particle story is one visualization, the fluctuating field story is another, and the mathematical formalism remains the same either way. This interpretational openness isn't a failure of physics, but a reminder that science gives us powerful tools for prediction and manipulation without always giving us a definitive metaphysics. The vacuum has properties we can measure. What it is at a deeper level remains a question. Let me return to the scale. Hierarchy, because it's worth emphasizing just how far removed the Planck scale is from anything we can currently probe. The highest energy particle collisions we can produce at the Large Hadron Collider reach energies of about 13 tera-electron volts. That sounds like a lot, and it is by human standards. The Planck energy, though, the energy associated with Planck scale physics, measures about 1.22 times 10 to the 19th giga-electron volts. Let me put that ratio in perspective. The LHC energy is about 1/10,000,000th of 1/10,000,000,000th of the Planck energy. It's like comparing the energy of a thrown pebble to the energy of a supernova. We're nowhere close. This explains why direct tests of quantum gravity are so challenging. The scales involved are so extreme that we can't reach them with any foreseeable technology. So we have to rely on indirect tests, like the gamma-ray timing observations that constrain space-time fuzziness, or look for subtle effects that might propagate down to accessible scales. Quantum foam, if it exists, does its thing at 10 to the negative 35 meters. We can barely probe 10 to the negative 18 meters with our most powerful machines, and the ratio is that staggering 10 to the 17th or so. This doesn't mean we'll never learn about Planck scale physics. Clever indirect tests, unexpected discoveries, and new theoretical insights could all open windows. It does mean we should be humble about claims regarding quantum foam and other Planck scale speculations, though. They're informed guesses about an inaccessible regime, not established facts. What we can establish, and have established, is vacuum physics at accessible scales. The Casimir Effect. The Dynamical Casimir Effect. The structure and properties of the quantum vacuum for fields like electromagnetism. This is real, tested, and tells us that empty space is not empty. Let me offer some thought experiments that might help make these ideas more vivid. Picture a box, a container you can evacuate perfectly. You pump out all the air, all the stray molecules, everything. You cool it to absolute zero, eliminating thermal radiation. You shield it from all external fields and particles. you create, as best as physically possible, a region of nothing. The classical answer holds that the box contains nothing, empty space, a vacuum in the traditional sense. The quantum answer differs. Inside the box, there are still quantum fields, the electromagnetic field, the electron field, all the other fields of the standard model. These fields occupy their vacuum states, the lowest energy configurations. But those vacuum states still have fluctuations, still have zero-point energy, still have structure. You can't remove the fields. They're not things that occupy space, but rather permeate space. And the very concept of inside the box relies on the space-time that the fields inhabit. Even your best nothing still contains the quantum vacuum with all its subtle activity. Here's another thought experiment. Picture zooming in on a point in empty space, magnifying by factors of 10 over and over. At the scale of meters, you see nothing, empty space. Zooming in by a factor of 10, still nothing visible. Keep zooming. At the scale of micrometers, you're in the realm where Casimir effects become measurable, where boundaries a micrometer apart feel forces from modified vacuum modes. You still see nothing directly, though, because the vacuum fluctuations are too subtle, too fast, too quantum. Zoom in further. At the nanometer scale, you're in the territory of atoms, but between the atoms is still vacuum, and the fluctuations are still there. Continue zooming. At the femtometer scale, you're inside atomic nuclei, seeing quarks and gluons. But between those particles, in the space they occupy, there's still the quantum vacuum, still the fields, still the fluctuations. Zoom in by another factor of 10,000. You're now at the Planck scale, 10 to the negative 35 meters. Here, if quantum foam is correct, space itself becomes uncertain, and the smooth backdrop you've been zooming into starts to fluctuate, to bubble, to become something strange. We don't know what you'd see there, though. We can't probe it and can only speculate based on incomplete theories. The journey from everyday emptiness to quantum vacuum to possible quantum foam is a journey through scales, from the familiar to the strange, from the tested to the speculative. Let me now ask you to think about what it means that humans have figured this out. 100 years ago, the quantum vacuum was not even a concept. The uncertainty principle was new in 1927. Quantum field theory was being developed through the 1930s and 1940s, and the Casimir effect was predicted in 1948 as an obscure theoretical result that few thought would ever be measured. Through a century of theoretical development and experimental refinement, humans have come to understand that empty space is not empty. We've built instruments that can measure the force exerted by modified vacuum fluctuations and shaken boundaries fast enough to produce real photons from the vacuum. Think about what that represents. Where biological organisms evolved on a small planet to find food and avoid predators. And yet, we've developed the mathematics to describe quantum fields, the technology to measure forces at the nanonewton level, and the insight to shake superconducting circuits at near light-speed effective velocities. This knowledge wasn't handed to us, but rather dug out through centuries of effort, building on each generation's work, making mistakes and correcting them, testing ideas against reality. The Casimir effect wasn't obvious. It had to be predicted and then the prediction had to be tested. The quantum vacuum wasn't a given, but emerged from the mathematics of quantum field theory, and the mathematics had to be worked out and checked. Human curiosity and persistence have extended our understanding into realms far beyond our everyday experience. We can't see vacuum fluctuations and can't directly experience the Planck scale, but we've found ways to learn about them anyway. This is the part that fills me with wonder. Not just that empty space is full of activity, but that we've learned this. That equations scribbled on paper predict forces we can then measure in laboratories. That theoretical speculation about space-time foam can be constrained by timing gamma-ray photons from distant explosions. The correspondence between theory and reality, the ability of mathematics to capture the behavior of the physical world, is not guaranteed. It's something we've discovered again and again at ever smaller scales and ever higher energies. Let me offer some numbers that might help you appreciate the precision of modern vacuum physics. The 2022 codata values for fundamental constants are known to extraordinary precision, with Planck's constant known to about 1 part in a billion. The speed of light is exact by definition. The Planck length is known to 10 significant figures. Casimir force measurements have achieved precision of a few percent, which might not sound impressive until you realize the difficulties. Separations maintained to nanometer accuracy. Surfaces characterized for roughness. Patch potentials measured and subtracted. Temperature effects accounted for. The Dynamical Casimir Effect experiments not only detected photons, but measured their correlations and statistics, confirming non-classical properties predicted by theory. These are not rough estimates or order of magnitude guesses, but precise measurements that agree with precise calculations. The physics works. Consider for a moment what it would be like if the physics didn't work. Picture experiments giving results that contradicted quantum field theory. The Casimir force coming out wrong, or absent, or reversed. That would have been a discovery too, perhaps an even more exciting one. It would have meant something new and unexpected about the quantum vacuum, and physicists would have had to figure out why. That's not what happened, though. The theory predicted a force, and the force was measured. The theory predicted dynamical photon production, and the photons were detected. Over and over, the framework has been confirmed. This doesn't mean quantum field theory is the final word. It might be an approximation to something deeper, just as classical mechanics turned out to be an approximation to quantum mechanics. Quantum gravity might reveal aspects of vacuum physics we haven't imagined. In the regimes we can test, though, the theory works. The quantum vacuum is real, structured, and measurable, which makes empty space a misleading term. Let me go deeper into some aspects we've touched on, because they deserve more attention. The uncertainty principle is one of those ideas that sounds simple, but has implications that take time to fully appreciate. Werner Heisenberg formulated it in 1927, and it fundamentally changed what we mean by knowing a physical system. Classical physics held an ideal of perfect knowledge. Given the positions and velocities of all particles at one time, in principle, you could calculate everything that would happen in the future and reconstruct everything that happened in the past. A clockwork mechanism, and if you knew enough, you could predict anything. The uncertainty principle says this ideal is impossible, not because of practical limitations, not because our instruments aren't good enough, but because of the fundamental nature of quantum systems. Certain pairs of properties, position and momentum, energy and time, cannot both have precisely defined values simultaneously. The mathematical statement holds that delta x times delta p is greater than or equal to manyship over 2. Delta x represents the uncertainty in position, delta p the uncertainty in momentum, and manyship is Planck's reduced constant, about 1.055 times 10 to the negative 34 joule seconds. That constant is small, which is why we don't notice the uncertainty principle in everyday life. For a baseball or a car or even a grain of sand, the quantum uncertainties are utterly negligible. For electrons, for photons, for the quantum fields that permeate space, though, the uncertainty principle dominates. Here's the connection to vacuum fluctuations. For a quantum field to occupy a state with exactly zero field value everywhere, with no fluctuation at all, would require the field to have both a definite value, 0, and a definite rate of change, also 0, since it's not fluctuating. These are conjugate variables, though, like position and momentum, and the uncertainty principle forbids them from both being exactly determined. The quantum field must fluctuate. Even in its lowest energy state, the vacuum state, some residual activity remains. Not because the field is being jiggled by something external, but because perfect stillness is quantum mechanically forbidden. This is a deep point worth pausing on. The vacuum fluctuations are not caused by anything in the ordinary sense. They're not the result of some disturbance or some outside influence, but a necessary feature of any quantum field, arising from the mathematical structure of quantum mechanics itself. Classical physics says the lowest energy state of a system is rest. A ball at the bottom of a bowl, perfectly still. A pendulum hanging straight down, not moving, zero kinetic energy, minimum potential energy. Quantum physics makes perfect rest impossible. The ground state still has energy, still has fluctuations, not because something is shaking it, but because that's what quantum mechanics demands. The zero-point energy formula, E equals 1/2 pendulum times omega, captures this. Even at zero temperature, even in the absolute ground state, half a quantum of energy remains in each mode. This might seem like a minor correction, a small addition to the classical picture. It changes the whole character of the vacuum, though. The vacuum is no longer absence, but a quantum state with properties, and those properties have consequences. Let me talk more about what it means for fields to permeate all of space. Quantum field theory proposes that every type of particle has an associated field. The electromagnetic field gives rise to photons. The electron field gives rise to electrons, and the quark fields give rise to quarks, with similar fields for all the particles of the Standard Model. These fields are not located in specific places, but exist everywhere. At every point in space, at every moment in time, there's a value for the electromagnetic field, a value for the electron field, values for all the other fields. When we say there's an electron here, what we really mean is that the electron field is excited at this location. The excitation is what we observe as a particle, but the field itself is everywhere. This is a different picture from the classical idea of particles as little balls moving through empty space. Quantum field theory treats the fields as fundamental, with the particles derived from them. The fields are always there, while the particles come and go as excitations of those fields. The vacuum state occurs when none of the fields are excited, with no particles anywhere. The fields remain, though, in their ground states, with their zero-point fluctuations. This is why empty space isn't really empty in quantum field theory. You can remove all the particles, all the excitations, but you can't remove the fields themselves. The fields are the underlying reality. Empty space still contains fields, just unexcited ones, and unexcited fields still fluctuate. Now let me explore the Casimir effect from a slightly different angle. I've described the Casimir effect as arising from modified vacuum fluctuation modes between conducting plates. This is the standard explanation, and it's correct. There are other ways to understand the effect that might give additional insight, though. One approach involves the concept of allowed and forbidden wavelengths. A quantum field can be decomposed into modes, like how a musical sound can be decomposed into component frequencies. In open space, all wavelengths are allowed, with no restriction on what frequencies the vacuum fluctuations can have. Put in two conducting plates, though, and those plates act as mirrors for the electromagnetic field. They create boundary conditions. The electric field must be zero at the surface of a perfect conductor. This boundary condition limits which modes can exist between the plates. Only wavelengths that fit are allowed, wavelengths where an integer number of half wavelengths spans the gap, and wavelengths that don't fit are excluded. Outside the plates, all wavelengths remain allowed, while between the plates only some are. This means there are fewer fluctuation modes between the plates than outside. Fewer modes means less vacuum energy density between the plates than outside, and a lower energy density inside than outside creates a pressure difference, pushing the plates together. The force tries to reduce the volume between the plates, because that reduces the region where vacuum fluctuations are suppressed. This represents a different way of stating the same physics, but it might help you see why the effect happens. The plates don't feel a force from nothing, but rather feel a force from the difference between something, the vacuum fluctuations, inside and outside. Let me give you another perspective using the language of virtual photons. In the virtual particle picture, vacuum fluctuations involve virtual photons appearing and disappearing. In open space, virtual photons of all wavelengths can exist. Between conducting plates, only certain wavelengths are allowed. This means there are fewer virtual photon modes between the plates. The plates are essentially squeezing out some of the virtual photon fluctuations, and this squeezing creates a net inward pressure. I want to repeat my earlier caution. The virtual particle picture is a visualization, a metaphor for the mathematics. The virtual photons are not real particles that could be detected. The picture captures something about the physics and can help develop intuition, though. The key point, regardless of which picture you prefer, is that the Casimir effect is a real, measurable consequence of the quantum nature of the vacuum. It's not just theoretical speculation, but experimental fact. Let me spend more time on the experiments. because the details are interesting. The original Casimir calculation was for two perfectly conducting parallel plates of infinite extent. This is mathematically convenient, but experimentally challenging. Real plates are finite, have edges, can't be perfectly parallel at nanometer separations, and aren't perfect conductors. The experimental strategy has been to use geometries that are easier to control, while still exhibiting the Casimir effect. Lamoureux's 1997 experiment used a sphere and a flat plate rather than two flat plates. A sphere naturally maintains a definite separation at the point of closest approach, so you don't have to worry about the plates being perfectly parallel, since the sphere-plate geometry is self-aligning. The experiment measured the force as the sphere was brought closer to the plate. The force increased as the separation decreased, following the theoretical prediction for the sphere-plate Casimir effect. The precision was impressive. Lamoureux reported measurements in the 0.6 to 6 micrometer range, confirming the Casimir force with enough accuracy to distinguish it from other possible effects like electrostatic forces from stray charges. Mohideen and Roy's 1998 experiment used an atomic force microscope, a device designed to measure extremely small forces. The AFM has a tiny probe tip on a flexible cantilever, and by bringing the tip close to a surface and measuring the deflection of the cantilever, you can measure forces at the piconewton level. Mohideen and Roy used this technique to measure the Casimir force at separations as small as 100 nanometers, 10 times closer than Lamoureux's measurements. At these smaller separations, the Casimir force is much stronger, and the measurements again confirmed the theory. These experiments launched a precision era in Casimir physics. Subsequent work has refined the measurements, accounted for more subtle effects, and explored variations. Real materials are not perfect conductors. They have finite conductivity, which means the electromagnetic field penetrates slightly into the material rather than being perfectly reflected at the surface. This penetration modifies the Casimir force, and the correction depends on the specific properties of the material. At non-zero temperature, there are thermal fluctuations in addition to quantum fluctuations. These thermal effects can be significant at larger separations and must be accounted for in precision measurements. Surface roughness matters too. Real surfaces are not perfectly smooth at the nanometer scale, having bumps and pits that affect the local separation and thus the force. Careful experiments characterize the surface roughness and correct for its effects. There are also electrostatic effects from patch potentials. Even nominally neutral conductors can have small voltage variations across their surfaces due to differences in work function or surface contamination. These create electrostatic forces that can contaminate the Casimir measurement if not properly controlled. The 2009 Review of Modern Physics article by Klimchitskaya, Mohideen and Mostepanenko synthesizes all of this. It reviews the theory for real materials, the experimental techniques, the various corrections and calibrations, and the state of agreement between theory and experiment. The bottom line? The Casimir effect is thoroughly established. Theory and experiment agree. The quantum vacuum is real and measurable. Let me now discuss something that might seem technical, but reveals something deep about the physics: the role of boundary conditions. In the Casimir effect, the conducting plates impose boundary conditions on the electromagnetic field. The field must be zero at the plate surfaces for a perfect conductor. These boundary conditions change which modes can exist, and thus change the vacuum energy. Boundary conditions are a central concept in physics. The laws of physics, like Maxwell's equations for electromagnetism or Schrödinger's equation for quantum mechanics, are differential equations. They describe how quantities change from point to point and moment to moment. But differential equations don't have unique solutions and need boundary conditions to pick out which solution applies to a particular situation. In classical physics, boundary conditions describe what's happening at the edges of your system. What are the fields at the walls? What are the initial conditions? In quantum physics, boundary conditions take on additional significance. They can change the nature of the quantum states, including the vacuum state. The Casimir effect directly demonstrates this. Change the boundaries, change the vacuum, change the forces. This suggests that the quantum vacuum is not just an abstract state that exists everywhere the same way. It's sensitive to the physical configuration, to what's around it. The vacuum between two plates is different from the vacuum far from any material. The vacuum near a curved surface is different from the vacuum near a flat one. This boundary dependence of the vacuum is something quantum, something without a classical analog. In classical physics, empty space is empty regardless of what's nearby. In quantum physics, the vacuum is shaped by its surroundings. Let me explore the connection between the Casimir effect and more familiar forces like the van der Waals force. Van der Waals forces are attractions between neutral atoms or molecules. They arise from the fluctuating electric dipoles in the atoms. Even though the atoms are neutral overall, at any instant the electrons are distributed asymmetrically, creating a momentary dipole. This dipole induces a dipole in a neighboring atom, and the two dipoles attract. Van der Waals forces are well known in chemistry and materials science. They explain why noble gases condense into liquids at low temperatures, why geckos can walk on walls, why certain materials stick together. Casimir effect is related to van der Waals forces. Both arise from electromagnetic fluctuations, and both involve forces between neutral objects. The Casimir effect can be seen as the retarded limit of van der Waals forces, valid when the separation is large enough that the finite speed of light matters. This connection was worked out in detail in the decades after Casimir's original paper. The 2009 Review of Modern Physics article treats Casimir and van der Waals forces together as aspects of the same underlying physics. The point is that vacuum fluctuations don't just create exotic forces in special experimental setups. They're connected to forces we already knew about from other contexts. The Casimir effect is part of a web of electromagnetic phenomena, all arising from the quantum nature of the electromagnetic field. Let me return to something fundamental and explore it from multiple angles. What does it mean to say that something exists in physics? When we say vacuum fluctuations exist, what do we mean? When we say virtual particles exist, what do we mean? These are not idle philosophical questions, since they have practical implications for how we interpret our theories. In physics, existence is often tied to observability. If something has measurable consequences, if it affects the outcomes of experiments, then, in a meaningful sense, it exists. By this standard, vacuum fluctuations clearly exist. They affect the Casimir force, can be converted into real photons, and have consequences. Virtual particles are trickier. In the formalism of quantum field theory, virtual particles appear in perturbation calculations. They're internal lines in Feynman diagrams. They're not directly observable in the way real particles are, though, and you can't build a detector that counts virtual particles. Does this mean virtual particles don't exist? The question might be poorly posed. Virtual particles are part of a successful mathematical framework that accurately predicts experimental results. Whether they really exist depends on what you mean by existence. Some physicists take a pragmatic view. The framework works, the predictions are accurate, and debates about the reality of virtual particles are philosophical rather than physical. Others take a more realist view. The framework describes something, even if our language for describing it is imperfect. Vacuum fluctuations are real, even if calling them virtual particles is a metaphor that can mislead. I tend toward pragmatism on these questions. The mathematics works and the experiments agree. What the theory is really about, at some deeper level, is a question we might not be able to answer definitively. What we can say is that the vacuum state is not trivial. It has structure, responds to boundaries, and its properties are encoded in the mathematics of quantum field theory. And those encoded properties lead to correct predictions about measurable phenomena. Let me now discuss some subtleties about how we measure and interpret the Casimir effect. The Casimir effect is usually described as a force arising from vacuum fluctuations. This is correct, but the precise interpretation requires care. When we calculate the Casimir force, we compute the vacuum energy with and without the plates and take the difference. The force is the negative derivative of this energy difference with respect to the separation. Here's a subtlety, though. The absolute vacuum energy is not directly measurable. What we measure is a force, which corresponds to an energy difference, a derivative. The absolute energy can be shifted by adding a constant to the energy, and such shifts don't affect the force. This is related to the renormalization procedure in quantum field theory. Infinities appear in the calculations and are removed by subtracting counterterms. The procedure defines what we mean by the vacuum energy, but the definition involves choices. Robert Jaffe's 2005 paper emphasized this point. The Casimir effect demonstrates that boundaries affect the vacuum. It demonstrates that there are measurable forces associated with these effects. What it doesn't do is uniquely determine the absolute value of the vacuum energy. This matters for questions like the cosmological constant problem. If we can't uniquely determine the vacuum energy from the Casimir effect, we can't use the Casimir effect to predict the cosmological constant. The two questions are related but not identical. The experimental situation is clearer than the interpretational situation. The Casimir force is measured, the measurements agree with theoretical predictions, and whatever interpretational subtleties exist, the effect is real. Let me also discuss some alternative derivations of the Casimir effect that don't explicitly involve vacuum fluctuations. In the standard derivation, the Casimir force arises from changes in the zero-point energy of the electromagnetic field when boundaries are introduced. There are other ways to derive the same result, though. One approach uses dispersion forces. The Casimir effect can be seen as the retarded limit of van der Waals forces between the atoms in the plates. From this perspective, the force arises from fluctuating dipoles in the material, not from vacuum fluctuations of the field. Mathematically, these approaches give the same answer. They're different ways of describing the same physics, but emphasize different aspects. The vacuum fluctuation picture emphasizes the quantum nature of the field itself. The dispersion force picture emphasizes the quantum nature of the material atoms. Which picture is really right? The question might not be meaningful. Both pictures are correct descriptions of the physics, complementary rather than competing. This is a common situation in physics. The same phenomenon can often be described from multiple perspectives, with each perspective illuminating certain aspects and obscuring others. The complete understanding comes from appreciating all the perspectives. Let me take you through the historical development of quantum field theory in more detail, because understanding how we got here helps appreciate where we are. The story begins with a puzzle. How does light work? In the 19th century, there was a fierce debate. Is light a particle, as Newton had suggested, or is it a wave, as Huygens and later Young demonstrated? The evidence strongly favored waves, since light shows interference and diffraction, phenomena characteristic of waves. Maxwell's equations, formulated in the 1860s, provided the theoretical framework. Light is an electromagnetic wave, a ripple in the electromagnetic field that propagates through space at a fixed speed. This picture was successful, but it had problems. The black body radiation spectrum, the distribution of light frequencies emitted by a hot object, couldn't be explained by classical electromagnetic theory. The calculation predicted infinite energy at high frequencies, a clearly wrong result called the ultraviolet catastrophe. 1900 brought Max Planck proposing a radical solution. He assumed that electromagnetic energy could only be emitted or absorbed in discrete chunks, quanta, with energy proportional to frequency. E equals h times nu. This assumption, made for mathematical convenience, reproduced the observed black body spectrum. Planck's constant h, the proportionality factor in his formula, measures about 6.626 times 10 to the negative 34 joule seconds. This tiny number sets the scale for all quantum phenomena. 1905 brought Einstein taking Planck's idea further. He proposed that light itself is quantized, that the electromagnetic field comes in discrete packets we now call photons. Each photon has energy h times nu and momentum h times nu over c. This explained the photoelectric effect, the emission of electrons from metal surfaces illuminated by light. Classical theory predicted that any light, given enough time, should eject electrons. Experiments showed that only light above a certain frequency could eject electrons, though, regardless of intensity. Einstein's photon hypothesis explained this. Each photon either has enough energy to eject an electron or it doesn't. Light is both a wave and a particle. A wave in the classical limit where interference and diffraction dominate, and a particle in the quantum limit where individual photon interactions matter. This wave-particle duality was the first hint of the strangeness of quantum physics. Through the 1920s and 1930s, quantum mechanics developed rapidly. Heisenberg, Schrödinger, Dirac, Born and others built the mathematical framework we use today. The Heisenberg Uncertainty Principle, the Schrödinger equation, the probabilistic interpretation of the wave function all came from this period. Quantum field theory emerged as physicists tried to apply quantum mechanics to fields rather than just particles. The electromagnetic field was the first target. How do you quantize Maxwell's equations? The answer involved treating the field as a collection of quantum harmonic oscillators, one for each mode. Each oscillator could be excited by integer amounts corresponding to 0, 1, 2, or more photons in that mode. The vacuum state occurs when all oscillators are in their ground states, with no photons anywhere, but each oscillator still has its zero-point energy. This framework, called quantum electrodynamics, or QED, was developed in the late 1920s and 1930s by Dirac, Pauli, Heisenberg, and others. It had problems, though, with calculations often giving infinite answers, which obviously couldn't be right. In the late 1940s, Feynman, Schwinger, Tomonaga, and Dyson developed the technique of renormalization, which showed how to systematically remove the infinities and extract finite, meaningful predictions. QED became a precision science, capable of calculating the magnetic moment of the electron to more than 10 decimal places. It was during this period that Casimir made his prediction about the force between conducting plates. His calculation was within the framework of QED, using the properties of the quantized electromagnetic field to derive a measurable consequence. The success of QED led to the development of quantum field theories for the other forces. The electroweak theory unified electromagnetism with the weak nuclear force. Quantum chromodynamics described the strong force binding quarks into protons and neutrons. The Standard Model emerged, a quantum field theory of all known particles and forces except gravity. Throughout this development, the vacuum played an increasingly important role. Vacuum fluctuations, vacuum energy, vacuum polarization. These concepts became central to how physicists understood quantum fields. The vacuum wasn't just the absence of particles, but a complex quantum state with properties that mattered for physics. This is the context for the Casimir effect. It's not an isolated curiosity, but a natural consequence of the quantum field theory framework that underlies all of modern particle physics. Let me return to the scale comparisons, because I think they help convey how extraordinary this physics is. The Planck length measures 1.616 times 10 to the negative 35 meters. This is so small that no measurement we can make comes close to probing it directly. For comparison, the wavelength of visible light is about 400 to 700 nanometers, around 10 to the negative 7 meters. That's 28 orders of magnitude larger than the Planck length. The size of an atom, roughly the Bohr radius, is about 5 × 10⁻11 meters. That's still 24 orders of magnitude larger than the Planck length. The size of a proton is about 8 × 10⁻16 meters, still 19 orders of magnitude larger than the Planck length. The highest energy particles we can produce at the Large Hadron Collider probe distances of about 10⁻18 to 10⁻19 meters. That's still 16 to 17 orders of magnitude larger than the Planck length. The Planck length is not just small. It's so small that it's hard to even imagine measuring anything at that scale with any foreseeable technology. This is why quantum foam, which supposedly operates at the Planck scale, is so speculative. We have no way to directly look at space-time at those scales, and can only infer things indirectly, through effects that might accumulate over large distances or long times. The gamma-ray burst observations that constrain space-time fuzziness work on this principle. If space-time fluctuates at the Planck scale, photons traveling through it for billions of years might accumulate enough of an effect to be detectable. The constraints from these observations are impressive, but they don't completely rule out quantum foam, and just rule out certain versions of it. Let me also put the Casimir Effect scales in perspective. The typical Casimir experiments involve separations of 10 nanometers to 1 micrometer. A nanometer is 10⁻⁹ meters, and a micrometer is 10⁻⁶ meters. These are small by everyday standards, but large by Planck standards. The ratio of a nanometer to the Planck length is about 10 to the 26th power. The Casimir effect operates in the nano world, which is a world of giants compared to the Planck scale. The Casimir effect and quantum foam are both about the quantum nature of space, but at vastly different scales. The Casimir effect is established physics in the nano world. Quantum foam is speculation about the Planck world, 16 or more orders of magnitude smaller. This scale hierarchy matters. When we talk about the quantum vacuum, we're sometimes talking about well-tested physics like the Casimir effect, and sometimes talking about speculation like quantum foam. The distinction is important. Let me share some more personal reflections on what it's like to contemplate these ideas. When I first learned about the quantum vacuum, really learned about it, not just the words but the concepts, it changed how I see ordinary space. The air in this room, the gaps between objects, the emptiness between the stars, none of it is what it appears to be. There's a moment when you're learning physics where the mathematics stops being abstract and starts feeling real. For me, the quantum vacuum was one of those moments. The realization that empty has a precise quantum meaning, that the vacuum is a state with properties, that those properties can be measured. This transformed an abstract concept into something tangible. I remember working through the Casimir calculation for the first time. The mathematics is not trivial, but it's manageable for someone with physics training. You sum over modes, you impose boundary conditions, you take a difference, and out pops a force. A force from nothing. It's not really nothing, though, and that's the point. The calculation reveals that the vacuum has structure that changes when you change the boundaries. The mathematics knows about something physical, something that shows up in careful experiments. This is the kind of moment that makes physics exciting. Abstract mathematics connecting to concrete reality. Predictions that can be tested. A universe that makes sense even when it's strange. The Dynamical Casimir Effect gave me a similar feeling. The idea that you can shake photons out of the vacuum, that vacuum fluctuations can be converted into real radiation, is so counterintuitive that it takes time to absorb. The experiments confirm it, though. The mathematics works, and reality is strange. I think there's value in sitting with these ideas, not rushing past them, letting them sink in. The quantum vacuum is not something you understand in one reading, but something you come back to, think about from different angles, gradually internalize. Let me offer some more numbers and comparisons to help anchor these ideas. The Planck time measures 5.39 times 10 to the negative 44 seconds. In 1 second, there are about 1.85 times 10 to the 43rd Planck times. That's more than a billion, trillion, trillion, trillion Planck times in a single second. If something fluctuates on the Planck timescale, it changes so fast that no conceivable instrument could track it. The fastest processes we can observe are many, many orders of magnitude slower than the Planck time. The Planck mass measures 2.176 times 10 to the negative 8 kilograms, or about 4.8 times 10 to the negative 8 pounds. That's about 22 micrograms, actually not that small by particle physics standards, about the mass of a grain of sand. The Planck energy, the energy associated with the Planck mass, measures about 1.22 times 10 to the 19 giga-electron volts. The Large Hadron Collider reaches energies of about 10 to the 4 giga-electron volts. The ratio is about 10 to the 15th, a million billion. To probe physics at the Planck energy scale with a particle accelerator, you'd need an accelerator a million billion times more powerful than the LHC. We are very, very far from being able to build such a machine. This is why indirect methods matter so much. We can't smash particles together at Planck energies, but we can look for effects that accumulate over cosmological distances and times. The gamma-ray burst timing observations do exactly this. Let me talk about what it means for science to have established facts and open questions at the same time. The Casimir Effect is an established fact. It's been measured by multiple groups using multiple techniques. Theory and experiment agree, and the physics is well understood. Quantum foam is an open question. It's motivated by theoretical considerations, constrained by observation, but not confirmed. We don't know if spacetime fluctuates at the Planck scale. We have speculations and limits, not answers. Both of these, the established facts and the open questions, are legitimate parts of science. Science isn't just a collection of known facts, but also a process of investigation, a way of asking questions and seeking answers. The established facts give us confidence. They show that our methods work, that theory and experiment can align, that we can understand aspects of nature far from everyday experience. The open questions give us direction. They show where more work is needed, where new ideas might make a difference, where the frontier lies. A healthy science has both. Too much certainty and there's nothing left to discover. Too much uncertainty and there's no foundation to build on. Physics, with its established framework of quantum field theory and its open questions about quantum gravity, has both. Let me step back and consider the philosophical implications of what we've discussed. The classical worldview, the one that dominated physics before the 20th century, was mechanistic and deterministic. The universe was a collection of particles moving through empty space according to definite laws. Given the initial conditions, everything that followed was determined. Empty space was just the background, the container in which physics happened. Quantum mechanics changed this picture deeply. Particles became probability waves. Determinism gave way to indeterminacy, and observation affected outcomes. Quantum field theory extended these changes to the vacuum itself. Empty space became the ground state of quantum fields, a state with structure and fluctuations and properties. The container turned out to have content. This is a significant shift in how we think about the physical world. The vacuum is not nothing, but something, a particular quantum state that happens to have no particle excitations, but still has fields, still has fluctuations, still has energy in some sense. Physics doesn't directly answer the deep philosophical questions about why there is something rather than nothing. Physics does change what we mean by nothing, though. If nothing means the classical void, empty space with no properties, then physics tells us this kind of nothing may not exist. The quantum vacuum is always there, with its fields and fluctuations. You can't have space without fields. If nothing means the quantum vacuum, then physics tells us this kind of nothing has properties. It can exert forces, can be converted into radiation, and is not featureless. I'm not saying physics answers the deep philosophical questions, but physics shapes the questions and changes what we're asking about. Any serious discussion of nothing and something has to grapple with what modern physics tells us about the vacuum. Let me also address something about the limits of our current understanding. Quantum field theory is extraordinarily successful. It accurately predicts the outcomes of experiments to many decimal places and underlies the standard model of particle physics, which describes all known fundamental particles and forces except gravity. Quantum field theory has limitations, though. It doesn't incorporate gravity in a consistent way. The calculations involve infinities that must be removed through the procedure of renormalization, and the vacuum energy calculation gives answers that don't match cosmological observations. These limitations suggest that quantum field theory, successful as it is, may be an approximation to something deeper. Just as Newtonian mechanics turned out to be an approximation, valid at low speeds, quantum field theory might turn out to be an approximation valid in certain regimes. What that deeper theory might be, we don't know. Quantum gravity research explores various possibilities, with string theory, loop quantum gravity, and other approaches, each suggesting different pictures of fundamental physics. Quantum foam is one speculation about what the deeper theory might reveal. If space-time is quantum at the Planck scale, the smooth manifold of general relativity would be an approximation, valid at larger scales, but breaking down at the smallest distances. We don't yet have experimental evidence for quantum gravity effects. The Planck scale is so far removed from what we can probe that direct tests seem currently impossible. But indirect tests, like the gamma-ray timing observations, can constrain certain models. This is the frontier, the established physics of vacuum. Fluctuations and the Casimir effect is solid ground. The speculation about quantum foam and Planck scale physics is uncertain territory, actively being explored. Science proceeds by building on what we know, extending into what we don't, testing predictions, and revising theories in light of evidence. The story of vacuum physics is part of this ongoing process. Let me return once more to the themes we've explored throughout this video. Empty space is not empty. The quantum vacuum is a state with structure, and vacuum fluctuations are real and measurable. The Casimir effect proves this. Two neutral surfaces in a vacuum experience a force from modified vacuum fluctuations, and the force has been measured with precision. The Dynamical Casimir effect extends this. Rapidly moving boundaries can convert vacuum fluctuations into real photons, and this has been observed in superconducting circuits. Quantum foam represents a speculation about what happens at the Planck scale. If spacetime is quantum, it might fluctuate like the fields do. This is not confirmed, but is constrained by observation. The scale hierarchy matters. Casimir physics operates at nanometer scales, while quantum foam would operate at the Planck scale, about 26 orders of magnitude smaller. These are vastly different regimes. Throughout, we've seen the power of theoretical prediction confirmed by experimental measurement. The Casimir effect was predicted in 1948 and confirmed with precision 50 years later. The Dynamical Casimir effect was predicted decades ago and observed in 2011. This is how physics works. Theory suggests, experiment tests, understanding advances. The quantum vacuum connects to many areas of physics. It's relevant to nanotechnology, to cosmology, to fundamental questions about the nature of space and time. Understanding it is not just an academic exercise, but has practical and philosophical implications. At the heart of it is a revision of what we mean by nothing. The classical void, the featureless empty space of Newtonian physics, is not the right picture. Quantum physics tells us that space has content, even when it has no particles. Fields permeate everything, and fluctuations never cease. This is what modern physics has revealed. It's confirmed by experiment, embedded in the standard model of particle physics, and stands as one of the surprising truths about reality that emerged in the 20th century. Let me close with a few final thoughts. Reality is stranger than we imagined. Every time physics has probed deeper, it has found unexpected complexity. Atoms are not indivisible, the vacuum is not empty, and time and space are not absolute. Reality keeps surprising us. Human curiosity has driven this exploration. From Heisenberg's Uncertainty Principle to Casimir's prediction to the latest superconducting circuit experiments, people have asked questions and built instruments and tested ideas. The understanding we have today is a monument to human ingenuity. the exploration continues. Quantum gravity remains unsolved. The Planck scale remains mysterious. And new experiments and new theories may reveal things we haven't imagined. The frontier keeps moving. You, watching or listening to this, are part of this story. You're engaging with ideas that took centuries to develop, contemplating questions that the best minds have puzzled over. The fact that these ideas are accessible, that anyone can learn about vacuum fluctuations and the Casimir effect and quantum foam, is itself remarkable. Take this understanding with you. The next time you look at empty space, know that it's not what it appears. Know that quantum fields are there, fluctuating, quiet, but not silent. Know that the simplest state of reality, the vacuum, is rich enough to study for a lifetime. The quantum foam exists, or it might exist, and we're working to find out. What we know for certain is that empty space does not exist, not in the classical sense. The quantum vacuum is something, not nothing. That's a strange and wonderful fact about the world we live in. It's been revealed by careful measurement and precise mathematics. And it's part of the scientific inheritance we all share. I hope this exploration has given you something to think about, some new perspective on reality, some appreciation for what physics has discovered and what remains to be found. Thank you for taking this time with me. These ideas deserve careful attention, and I'm grateful you've given them yours. The space around you hums with quantum activity. The vacuum is alive in its quiet way. Tomorrow, somewhere, scientists will continue the work of understanding it better. If you found value in this journey, consider subscribing to the channel. There are more explorations like this, more opportunities to engage with deep questions about the nature of reality. And we'll continue to learn together, to think together, to wonder together at what physics has revealed and what remains to be discovered. Sleep well under the stars. The emptiness between them is full of secrets we're still uncovering. Good night.